Hi everyone, and welcome to another video on random processes and LTI systems. In this case, we're going to build on the example we did in a previous video and look at some Matlab simulations and try and build further intuition about what's going on. So in the previous video, we considered a real wide-sense stationary zero mean IID process going into a discrete time LTI system. So the input autocorrelation was just delta vel, sigma x squared delta vel, where sigma x squared is the variance of the noise going in. And we ran it through an example system, right, which was this simple FIR system, which has an impulse response that's equal to 1 at 0 and 1 at 1 and 0 everywhere else. So it's a 2-point finite impulse response system. And we previously showed that the output will be a real wide-sense stationary process with zero mean and with this autocorrelation function. So the autocorrelation outside of lags plus and minus 1 is equal to 0, and this is what it looks like for lags minus 1, 0, and 1. Now, I'm going to show you some Matlab examples, and we're going to assume that we have Gaussian IID noise, right? So here we didn't have to assume anything about the process other than it was the same distribution at each time point. Here we're assuming it's Gaussian for the examples, and that sigma x squared will be equal to 1. Okay, so here's what I did. I created some realizations of this random process. Again, I'm assuming that we have zero mean IID Gaussian noise where the variance is equal to 1. And so Rx of L is just delta of L. And I've generated 1,000 realizations. What you see here is, really dot, 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 right? This is the first realization. This is the 1,000th realization. I'm only showing you the first, the second, and the 1,000th. There are 997 more of them that I could have plotted, but didn't plot in this space in between. And so you see I've generated a series of time points for each of these, right? I'm just generating from over a range of n values, right? So each of these points in here is an independent draw from a Gaussian random variable. So let me just highlight here at n is equal to 5. Okay, so I'm just highlighting here at n is equal to 5, right? So this is x of 5. Right. So now what I'm showing you on this plot here is a scatter plot of all of these points just at n is equal to 5. Okay. So the scatter plot goes along here. So it's just all of these values scattered along this axis. And for reference, I've plotted a Gaussian random Gaussian PDF along here, right? Which says, okay, the probability. This is the probability density function, so I'm expecting more points in here than I am way out in the tails, which is exactly what I see from these 1,000 random draw in here. Again, so I'm taking the 1,000 points just at n equal 5 and scattering them like that, and it obeys what we expect. Okay, so now I've got the same exact realizations that I showed you on the previous slide. And here's our n equal 5 point, right? So those were the points I scattered before. Now I'm going to do some 2D scatter plots. Okay, so the first 2D scatter plot I'm going to do is I'm going to take all the points at n equal 5 and all the points at the previous value, n equal 4. And I'm going to scatter those versus one another. So here is all of these realizations here are on the x-axis. This is the blue, the x of n0, which is n0 is 5 in this case. And then I'm going to plot that versus the points at n equal 4, right, which is these set of points, right? And so we get this sort of circular scatter plot, which is what we would expect because these points are uncorrelated from one another, right? This is IID, right? IID, if they're independent, they're definitely uncorrelated, right? And they're Gaussian, right? So we expect this sort of circular plot, right? And we could draw an ellipse on here, and this ellipse would be a circle in this case. And the concentration ellipse, right? Because these are two independent Gaussian random variables. Okay. Now I just did it to show one more case. I'm going to take all of these points, the n equal 5 points, and scatter them versus the n equal 3 points, right? So 2 points earlier. Well, all of these are independent, right? From here to here is independent, from here to here is independent. So we expect that to have the same same uncorrelated looking scatter plot for this bivariate Gaussian, okay? So they're different points here, right? Now I still have all of these same points, but now they're scattered, right? So my sort of pair that describes how far it goes on the horizontal and the vertical, right? This is the horizontal point, this is the vertical point in this graph. So we can see, yeah, everything looks uncorrelated, and I could continue doing these with different pairs, right? With something along here, something along here. I would continue to get uncorrelated looking scatter plots, and they all have variance, right? The same variance. So this looks like a circle here because these points have variance 1, these points have variance 1, these points have variance 1, etc. Okay, so now I'm going to take those realizations, those 1,000 realizations, but I'm just, again, showing you 3 here, and I'm going to run each realization through my discrete time LTI filter, so through this 2-point FIR filter. So I run this realization through, and this is what I get out. I run this realization through, this is what I get out. Run the 1,000th realization through, that's what I get out. Okay, and I know that my input autocorrelation was just delta of L, right? Because it's uncorrelated. And I know my output autocorrelation should be this. Okay, so what am I expecting here, right? The variance, since, again, these are zero mean, so the autocorrelation at lag 0 is equal to the variance of the random variable. Now, instead of being 1, it's 2, right? So I should expect a higher variance coming out, which I see reflected in these plots if I take a careful look at them. And also what I've done here is I've said, okay, I'm going to just look at these points here at 5 again and do my 1D scatter plot. So now I'm plotting the output at n equal 5 and along with a scatter along this axis, right? And this also looks Gaussian, right? If I have an input that's Gaussian to an LTI system, I will get an output that is also Gaussian because the sum of Gaussians is also Gaussian. Now it's got a wider variance, right? This had a narrower PDF, right? It had variance 1. With a larger variance, this should have variance 2 based on this. I'm more spread out along here, right? So I get a larger variance, and they're distributed along here as we would expect for a Gaussian random variable with variance 2. Okay. Okay, so now I'm going to look at some 2D scatter plots of the output. So just like before, I'm just refreshing your memory of how these looked before. This is if I scattered all of these points at n equal 5 against all of the points at n equal 4. I got this uncorrelated scatter plot, right? Variance 1, and this variable is uncorrelated from this variable. Now if I look at the output, and I look at n equal 5 at the output and n equal 4 at the output, and I scatter these two sets of points against one another, now I get a different picture, right? These are now correlated. These are now correlated because these 2 points are non-zero, right? They have a positive correlation. They have a positive correlation. And this is what I would expect, right? So because they're positively correlated, when this point is larger, this point tends to be larger. So that gives us a tilt to this scatter plot here. And the other thing we notice is this scatter plot, right, is wider than this scatter plot, right? Why? Because we've got a larger variance of this random variable, right? We've increased the variance by running through this LTI system, where basically the output, remember, is just the sum of, right, for this system, the output is equal to x of n plus x of n minus 1. That's what we derived before. Okay, so that's what this looks like. So we put in uncorrelated data that was uncorrelated along the time axis here, n, and we get out correlated data due to the fact that we're running it through a convolution. Running it through this convolution means each output point depends on the current value of the input and the previous value of the input. So these two have to be correlated. Now I'm showing you one additional scatter plot here. So these are the scatter plots that I showed you on the previous page, right? These two. But now I'm at the output here, I'm going to do a new scatter plot where I scatter this set of points and this set of points, right? So along the x-axis is all of these points, and along the y-axis of this graph, it's all of these points, right? Now this is a circular scatter plot, right, which suggests that it's uncorrelated data. Does that make sense? Well, hopefully it does, right? These are at lag 2, right? This is y of n0 minus 2. This is y of n0. So this is 2 points previous. Well, 2 points previous in the output doesn't depend at all on the current output because, again, remember, right, y of n is x of n plus x of n minus 1, right? So it doesn't depend on x of n minus 2 at all. It doesn't depend on 2 points previous. And so that's why this will be uncorrelated. So these two values are uncorrelated while these two values are correlated, right? And if I shifted along and I took any two, I could shift this over and be looking at points at 8, 7, and 6, and we would see the same pattern. 8, all of the points at 8 would be uncorrelated from all the points at 6, right? If lags greater than 1 are uncorrelated, right, because of the zeros in this autocorrelation. So here's a quick summary, right? The input, right, we had an input of a wide sense stationary random process that was IID, so it was a white noise process here, and went into this system, a 2-point FIR system, and came out, right, it went in uncorrelated, came out correlated, right, correlated over a short time, right, correlated at lag 1, uncorrelated outside of that. And these correlation sequences, right, both at the input and the output, dictate what we see in these scatter plots. At the input, we get things are uncorrelated, right, no matter what set of lags we look at, right? N0 was 5, so this is x of 5, this is x of 4, this is x of 5, this is x of 3. These are all uncorrelated at the input because of this autocorrelation sequence. Once we run it through the system, now points that are located 1 point apart are going to be correlated. So x of 5 or y of 5 is correlated with y of 4, right? But y of 5 is not correlated with y of 3, okay, because of this autocorrelation sequence. And again, remember we used basically this this general expression to compute the relationship between the output autocorrelation and the input autocorrelation. But hopefully this gives you some better picture using 2D scatter plots, right, which we use to display data that is bivariate Gaussian, meaning that the points are jointly Gaussian. And we use it to display whether they're correlated, right, which would be this case, or uncorrelated. So hopefully this gives you a better picture and something to work on in the future. So if you want, right, here's a good challenge problem for you. So challenge problem that you can think about on your own. What changes if h of n looks like this, 1 and minus 1 instead of 1 and 1? So what would change in these scatter plots if you changed the impulse response? If you change the impulse response here. And you can do this, you can easily implement this in Matlab or in Python. Run uncorrelated Gaussian noise through an LTI system and do it multiple times to create many realizations, and then you can create scatter plots like this. So hopefully this has given you a bit more intuition about what autocorrelation means and how to tie together both the random processes material we've done with the bivariate Gaussian and the simple scatter plots that we've done. Thanks for watching.